Okay, so I guess it's time to start. So your attention, please. So today we will continue our journey through the physical layer and talk about error probabilities and so forth. So this requires us to do some assumptions on the channel noise and the transmitted bits and so forth. Last week we talked a little bit about how we can look at bits as being random quantities. And today we will continue to talk a little bit about the channel noise and make assumptions about the randomness of that. And from these two assumptions we can actually calculate probability of making various types of errors. Okay, but to review, so what we talked about last time was to, among other things, if we have a pulse amplitude modulation, we have a pulse shape H, and we have a symbol alphabet curly A, A1 through AM. And now what we would like to do is to calculate the energy per symbol, the average energy per symbol. Okay, so which is basically the energy we need in order to transmit the bits which belongs to one symbol. So if the bits are equally likely and independent transmitted, equally likely and independent, then we know that A, the amplitude, is uniformly distributed over these amplitudes. So all of these amplitudes are equally likely. So they are transmitted with probability 1 over m. And then we can then calculate the average energy per symbol as the product of EH and EA. And EH is the energy of the pulse, and EA is the energy for the constellation, which is defined as the expected value of the magnitude squared of the transmitted amplitude. And here, the assumption here is that A here is a random variable that takes on values inside this set with equal probability. Okay, so and that comes from the assumption that the bits that we transmit are equally likely and also independent of each other. Okay, so this is the new thing here, and what I would like to stress also is that the E here is the expected value, so it's no energy or anything like that, so it's an operator. Okay, and since these are equally likely, they occur with probability 1 over m, and then we just sum the square of the possible outcomes of the amplitudes, and then we get the energy for the constellation. Okay, so what use do we have of this energy per symbol? Well, that is related to the transmitter power we need for communication. So the average transmit power or transmitted power is P, and it's directly proportional to ES, the energy per symbol, and then divided through by T, where T is the time between symbols. So one can think of it that the transmitter is a device that outputs the energy ES, and it does that every T seconds. And therefore, the power required of the transmitter is the ratio between the energy and the time. So you remember that power is energy per time unit. So we need to fix what is in the numerator, what is the energy, and what is the time. Okay, so if the energy is the energy per symbol, then the time is the time between symbols. If the energy is the energy per bit, then we should divide through by the time between consecutive bits. Okay, so actually, this equation here is of course equal to this one, where the symbol rate is 1 over t. But this one extends also to energy per bit and the bit rate. And we didn't show that explicitly last lecture, but it's a quick calculation because we know that RB is related to RS or t as the log 2 of m divided by t. So log 2 of m is the number of bits per symbol. Therefore, is the bit rate the number of bits per symbol times the symbol rate. Okay, so log 2 of m times RS. Okay, and the energy per bit then, what is that? Well, it's the energy per symbol, right, divided by the number of bits there is per symbol, which is then log 2 of m. And then combining this equation and this equation, we just multiply them together, we see that the log 2 of m cancels, and we're back to ES times RS. Okay, so it's very quick derivation of this. But in general, one can say that if we have a device that has a power P and it outputs something, then the energy for that something divided by the multiplied with the rate of which we transmit that something, that is always constant, equal to the power. So P here is equal to ES times RS, or EB times RB, or some other energy times its rate. Okay, so it extends through this logic. Okay, then let's continue then our journey here. So now we know a little bit about the energy per symbol and the power of the transmitted signal, and we will see how that comes into play when computing the error probability a bit later. One thing that we will be very concerned about shortly is Gaussian or normal random variable. So normally distributed random variable or Gaussian random variable is the same thing, right? So in this course we will call them Gaussian random variables. I'm sure you've seen this before, but maybe not in this notation. So let's go through the notation. So if x is a Gaussian random variable, we say that this curly wiggle here means distributed as, and then curly n means Gaussian or normal, n for normal, I guess. And the first quantity here is the mean, and the second one is the variance. Okay, and I would like to stress that it's the variance, because we also see notation where it's sigma as the second second parameter in this notation. We're not going to use that in this course, but if you look in other books, you might see this. Okay, so mu here is simply the expected value of x, and sigma squared, it is the variance. And remember that the variance is the expected value of x, subtract off its mean, square it, and the expected value of that is the variance. If we're interested in the PDF, it's this Gaussian bell shape. You've seen it a billion times. Oops. You've seen it a billion times before, right? It's some bell curve that goes like this. Right? It's not very pretty drawing here, but essentially the midpoint here is mu, and then basically the width of this one is proportional to sigma squared. Okay, so the width of the PDF depends on sigma, and the center point of the Gaussian bell shape depends on mu. Okay, so this is fx of u, or this is u. Okay, now for a Gaussian random variable, if we have ax plus b, where a and b are constants, then this is also a Gaussian random variable. And the difference is that this now the average has been shifted to be a times mu plus b. And interestingly enough, the variance is not dependent on b, but only on a. So the variance is a squared times sigma squared. Okay, so this is a useful equation later on when we have Gaussian random variables and we multiply them with constants, and we're interested in the distribution of that one. So one specific translation we would like to do is to take x and subtract off its mean and divide by its standard deviation. Okay, recall here, see now it's sigma, not sigma squared we divide through. And if we do that and we just plug that into this formula, we see we get a standard Gaussian random variable. And a standard Gaussian random variable has mean 0, variance 1. Okay. Are we cool so far? Right? This is news or old stuff or what?
Old stuff.
Old stuff. Okay, let's go. So Q function. You've seen Q functions before, but maybe they were not called Q functions. So Q function, Q of x is the probability that y is greater than x, where y is a standard Gaussian random variable. Okay, so it has mean 0 and variance 1. So if we plot the Gaussian PDF, it's this bell shape here, and then Q of x is the probability that the Gaussian random variable exceeds this value x, and we get that by integrating the tail of the Gaussian PDF here. So Q of x here, if we think of it, it's almost like a CDF, but the other way around. the CDF would be the integration of whatever is to the left of x. So sometimes q of x is called the complementary CDF. But we will just call it the q function. Okay. So by definition, it's this integral here. And you don't have to integrate this in MATLAB. You just use the function qfunc. Okay, so it's implemented for you already in MATLAB. Now, if z is a Gaussian random variable with some mean mu and some variance sigma squared, mu z or sigma squared z, then if we want to calculate these probabilities, and these probabilities we are sometimes very interested in, the probability that z, a Gaussian random variable, is greater than x, how can we use a q function in order to figure this one out? Well, first we do a transformation of the left-hand side and right-hand side of this inequality, and that doesn't change the value of the probability. So what we do is we take z, we subtract off its mean, and divide by the standard deviation. And what we have then to the left-hand side of the inequality is a standard Gaussian random variable with 0 mean and variance 1. And to the right-hand side, we do the same transformation. So here we just have another number now, x minus the mu and divided through by the standard deviation. And since we have this type of probability, which is actually the definition of the q function, we can simply plug in the right-hand side of the inequality into the q function to get the value of the probability. So here, we simply take this. Oops, that was a poor drawing. We simply take this thing, and we plug that into as the argument of the q function, and boom, we have the probability. Okay. So whenever you have a situation like this, that you need to calculate the probability that a Gaussian random variable is greater than some number, you can do an easy transformation and use the q function. So according to this, very, very useful. Okay. Now, let's go to some other mathematics that you've probably seen before, but let's just reinforce that. The Dirac delta function, you already seen this in this course in terms of the impulse response of a continuous time, linear time invariant system. So the impulse response is the output when the input is a delta pulse. So what is a delta pulse? Well, actually mathematically it's quite complicated object. But we're not going to go into the mathematics here. We're just going to be engineers and say that this is a very thin and very high pulse. Okay, so that's our delta pulse. So engineering interpretation is quite simple. Delta pulse is a very thin and very high pulse. Okay, so if we think of this as that we start with a square pulse like this, which has an extent here, a duration here, which is epsilon, and a height, which is 1 over epsilon, which tells us that the area here is equal to what? Thank you. Friday afternoon, can still integrate square pulses. Great. It's going to be a good weekend. All right, and then we just let epsilon be very small. Okay, so what's going to happen is that the base of this will shrink and the roof will go up, right? So then we get, in the extreme case, something which is extremely thin and extremely high, but still have area equal 1, exactly. So it's a little bit special, right? Okay, so so when epsilon goes actually to 0 here, this becomes a very strange object. So we can stop somewhere where epsilon is small enough for our purposes, but still not 0, or not even close to 0. Okay. The main property that we will use for the delta function is something called the sifting property. Sifting means a sift is a sil in Swedish. Man silar fram någonting. Okay. So sifting is pulling out something. It's something also called the sampling property. So if we have some nice function f of x here, which is not discontinuous, just something we can draw, right? So f of x, I don't know, it's, something like that, f of x. And then if we take f of x and we multiply that with the delta function, who's centered around x0, maybe around x0 like this. So we have our delta function here. Then if we look at, and then we take the product of the delta function and the regular function, and we integrate that for all times, then we get the value of the function at the time where the delta pulse is non-zero. Okay. And we can sort of believe that that is the case, because if I form the product of f of x and this delta function here, I get the delta function here multiplied with the value of the function at that time. And since we agreed upon that the area of the delta function is 1, the area of the delta function plus multiplied with this function here should be then the value of the function. So when we integrate here, we get the value of the function. Okay, super fast and not very rigorous argument there, but that's essentially what's going on. Okay, so delta functions are beautiful things when we put them inside integrations, because all of those integrals are super simple to solve, right? We just need to consider the value of the integrand at the point where the delta function is non-zero. Okay, and we forget about the delta function there. So the value of the integrand except the delta function at the x where the argument of the delta function is 0. So for instance, if I convolve f with the delta function, I simply get f, but then time shifted to the time where the delta function is non-zero. Very useful property. Okay, so far? Cool, let's go on. Now, back to our problem here. We have pulse amplitude modulation, and we transmit a signal S over a channel which adds noise. So now the focus here of the development is on the noise. What is the noise going to do to us? Previously, we have talked a little bit about how to how to choose the pulse shapes, T, and so forth to get intersymbol interference-free transmission. So let's assume we've done that job, right? Which means that if we forget about the noise, AK here will be showing up at this point in the block diagram. Okay, so everything is great if we don't have noise. Now, if we have noise, then the noise is going to propagate through this filter, and after sampling, we will have a noise contribution in Y. And we need to figure out now, what is the noise contribution? In particular, what is the distribution of the noise contribution? Because we will model the noise as being random. Okay, so that's the objective now. And to go things a little bit ahead, we will show later on that Z of k is equal to AK, which is the thing we would like to, because, okay, AK is what we're looking for, so that's good, but it will also continue, it will also contain an additive term due to the noise, NK. Okay. And later on we will show that NK is a Gaussian random variable with 0 mean, and let's see, some variance sigma squared. Okay, we will show that later on. And the issue now is to figure out what sigma square is. Okay. To figure out what sigma square is, we need to figure out, or we need to describe the noise here. And if we want to find the worst possible noise we can ever imagine, then that is known as white Gaussian noise. So it's sort of like a worst case assumption on the noise. And if we do that, okay, so what is white Gaussian noise? First of all, it's a random process, and we will talk about what the random process is later, but essentially it's a sequence of random variables. And all of these random variables are zero mean Gaussian random, and it has an autocorrelation function which is equal to this, and we will talk what the autocorrelation function is in a second. And this n naught over 2 is a constant, it determines the strength of the noise. Okay, and the reason why we divide by 2 here is of historical reasons, but it's been like that since many years. So n naught over 2 is the standard assumption for this. So let's continue with this. Okay, so let's talk a little bit, first of all, what is a random process, what is an autocorrelation function, and what happens when we filter this noise, and what happens when we have sampled it. And then we can arrive to nk. Okay, so that's basically the storyline going forward here. Okay, so we start with random processes. Just a short, how many have heard of random processes before or had a course in that? 1, 2, 3, 4, okay. Very good.
What's the Swedish?
Stochastic process. You heard of it?
Yes.
Okay, good, very good. Okay, so a random process is essentially a sequence of random variables. So if R of t, sorry, wrong notation. So if x of t, capital X of t, is a RP, random process, then for every fixed t, say when time is equal to t1, x t1 is a random variable. Okay, so let's look at this statement here. X of t, where we don't specify t, so t could go from minus infinity to infinity. Okay, for all, that's just a whole random process. If we fix a time, we look at the random process at one specific time, that is when t is equal to t1, then x of t1, this is a number. Okay, this is a function, or actually a random process, and this is a random variable. Okay, that can take on random values in some set. So we have here a random variable, x of t1. Okay. If the expected value of x of t, which is mu, some average, in general, this depends on at what time instant we look at. So it's a function of t, typically. In general, that is the case. So the expected value of x of t, where we don't specify t, depends on t, so it's a function of t. But if this is equal to mu, a constant, and the expected value of x of t multiplied with x of t plus some number tau, this is typically a function of t and t plus tau, the two time instances. Okay. In general, x of t is a random variable, and x of t plus tau is another random variable. The distribution of the first random variable and the second random variable typically depends on t and t plus tau. So the expectation here should be some function, let's call it capital R, of t and t plus tau. So that is in the general case. But if this, with a little bit of abuse of notation, can be written as R of tau, we have special properties of this random process. Namely that then x of t is wide sense stationary. Or in Swedish, svagt stationär. So we have a random process. If its average does not depend on time, and if this, which is the autocorrelation for x, does not depend on t, but only on the spacing between these two times, namely on tau, then we say that x of t is White-Sands stationary. So what does that really mean? Well, it means that we have a random process that somehow does not change in time. Okay, it's something whose statistical properties does not change in time. So it really doesn't matter too much. So, for instance, if I listen to let's leave it at that at the moment, right? Okay, we continue. So we talk about white processes also. So a process is white. A random process is white if the autocorrelation function, or ACF, has the form so Rx of tau, okay, which is the expected value of x of t plus tau. Okay, so this holds in general. This is the autocorrelation function. And okay, so a process is white. It has also to be, it's White-Sands stationary by assumption. Okay. If this happens to be some scaled version of a delta pulse, then we say that the process is white. So to illustrate this, we think of the autocorrelation function for a white process, which we plot as a function of tau, is a scaled delta function, which is non-zero at tau equals 0. So we have here this delta function. So this autocorrelation function is some constant k times delta of tau. Okay, so the reason why this is called a white process is actually the following thing, that if we take the Fourier transform of this, we get something called the power spectral density, and tells us how the power of this function, how this random process is distributed in frequency, and it actually turns out to be a constant. And you know that light with the constant intensity over all frequencies is white light. Okay. If you split it up into all different frequency components, you get reds and blues at the low and high frequencies. But if it contains all frequencies with the same intensity, we perceive it as white. That's why this is called a white process. Okay. Now, the channel noise that we have is usually modeled as white Gaussian noise. So it's a white process where all the random variables in the process are Gaussian. So we have additive white Gaussian noise, Okay, additive is not so important. It just means that the channel, what it does, it adds this type of noise to the transmitted signal. So white Gaussian noise, what can we say about that? Well, if that's the NOT that we had on the slide previously. So additive white Gaussian noise, it means that n for some time t1 is a Gaussian random variable. And it means also that the autocorrelation function for the noise signal, capital R of n, as a function of tau, which by definition is the expected value of n of t multiplied with n of t plus tau, is n0 over 2 times the delta function of tau. Okay. So what I said previously that this is sort of like the worst type of noise that we can imagine. So if we can do a good communication system with this noise, we should be okay with other types of noise. So what is so bad about this? Well, first of all, what is the variance of a noise sample here? Okay, so the variance, we know it's zero mean. White means also that the signal has to be zero mean. So it's a zero mean, but what is the variance? Well, the variance we get by taking the autocorrelation function here and inputting tau equals 0. Okay, so what is then the variance? Well, I claim it's equal to R of n, the autocorrelation function, where we put in tau equals 0. So what is this? N over 2 times, which is, no. Yeah, here we go. So it's n0 over 2 times infinity, which is equal to infinity. All right. Now let's see here. We have some noise whose variance is infinite. Is that a physical model of noise? No. If I had this noise source, there will be no energy problems on Earth, right? Because here we have a power source of infinite power. Beautiful. We could use that. But what I'm trying to say now, that there is no white noise in the physical reality. So it's a mathematical model of something which has a lot of variance in it. Okay? So if we would plot this noise signal here, first of all, it would be widely oscillating like this, because there is no correlation between two samples. I mean, the noise at one time does not tell us anything about the noise at some other time. And also, the variance here would be infinite. So actually, it will never be capped like it is like this. It will go up to infinity and down to infinity. So this is how white noise looks like. It's actually black, right? So if you will plot it, you would not see the trace of it. Okay. So this is the worst type of noise we can imagine. It's very high amplitude and very erratic, goes up and down, up and down, up and down, or in no pattern, by the way, right? So we can never predict it. So it's a really, 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 really bad noise. Okay. But still, we are fearless and we will defeat this. Okay. So let's see how we can do that. And actually the key to the success here, which is very surprising, is that when we filter white noise, we can make the output to have finite power. So the input has infinite power because of this variance, which goes up and down from minus infinity to infinity, so it has infinite power. But when it goes through a filter, it has finite power. So this is a very surprising thing, but it's good for us because what we want to do is to filter the received signal. That's the first thing we do, right? Is to do this. So surprisingly, if we take this horrible white noise and then feed it through a filter with some impulse response, let's call it H. And then look at the output, WT. What can we say about WT? Well, it's the convolution of the input with the impulse response. So WT is N of t convolved with H of t, which is an integral from minus infinity to infinity, n of, well, let's pick u, and then h t minus u du. Okay, so we know, what do we know here? Well, we know that the noise, this term, is white and Gaussian, so it's a Gaussian random variable. For each value of u, we get a Gaussian random variable. So if we look at the integrand here for a fixed t and u, what can we say then? Well, we have n of u multiplied with h t minus u, and h here is a regular signal, right? So h t minus u is just a number, 3, 45 minus 72 or something. It's something, right? And then we have a Gaussian random variable here. So what is the product of a Gaussian random variable with a constant? What is that random variable? What type of distribution does it have? Gaussian, exactly. So if we take a Gaussian random variable, multiply it with 42, we still have a Gaussian random variable. It doesn't matter what we multiply it with, we still have a Gaussian random variable. Now, so what we can say here is that what we have inside here is Gaussian. So it's Gaussian random variable. Now, what can we say about the integration here? Well, integration is essentially a summation, right? So we basically sum the integrand's values over the integration interval. So think of the Riemann sum. The integral is the Riemann sum where we make the step size go very small. So we can think of the integration here as a sum. So what we have here, for a fixed t, we have a sum of scaled Gaussian, we have a sum of Gaussian random variables. So what is the distribution of a sum of Gaussian random variables? Gaussian. Here we go, Gaussian. So great. We have here something which is Gaussian. So the good thing about Gaussians is that we only need to figure out the mean and the variance of it to fully specify it. So let's do that. It's not difficult actually. So the average of WT, the expectation of WT, then we use the linear properties of the expectation. So this is simply the expected value of this integral, n of u h t minus u du. So it's the expected value of the integral. And since we have a expectation is linear, a linear operator, we can write this as the integral from minus infinity to infinity of the expected value of n of u times ht minus u du, like this. So we just pull in the expectation inside the integral, and then we pull out the h, because h is not random. The only thing which is random in the integrand is n of u. Okay? And what is the expected value of n of u? Do you remember? What was the average value of the noise? The mean of the noise? 0. Okay, so this is 0. So the integrand is 0, and it doesn't matter how much we integrate 0, we still get 0. Okay, good. So mu, the output, the mean, the average of the output is 0. Okay, so now we just have the sigma square to figure out, and it's actually a little bit more complicated. So I need a full column to do that. So let's write it like this. Okay, so the expected value of w squared of t, what is that? Well, let's just write it out. It's the expected value of w squared, and w is the convolution between the input and the noise, which is the input, and the impulse response. So it's an integral. So the square is just a multiplication of two integrals. So we have the expected value of an integral nu h t minus u du. Okay, so this is w of t. And then we want to multiply that with w of t, so which is another integral from minus infinity to infinity. Now we need to pick another integration variable, so let's pick v instead. So it's n of v h t minus v dv. Okay, so give ourselves a little bit more space. Okay. Okay. Now we make this into a double integral and collect all the randomness here, which is n of u and n of v. So we have now an integral from minus infinity to infinity, and then an integral from minus infinity to infinity. The expected value, and inside the brackets of the expected value operator, we put in everything which is random, which is n of u and n of v. Okay. And the rest, the h factors here, are all deterministic, that is non-random things. So we'll just put them out. So we have here h t minus u, and then du, we do this, and then we put some brackets like this, and then we have h t minus v dv, like this. Okay, so now we take the knowledge we have about the autocorrelation function of the noise, because what we have here is by definition the autocorrelation function of the noise evaluated at u minus v, the difference between the arguments of the n function. Okay, which is, we know that is n naught. By the way, n0 in English becomes n naught, not for subscript 0. Okay, it's just the way it's said sometimes. So n naught over 2. And then we have a delta function, and it's with argument u minus v. Okay, and now great happiness in the room, because we have now an integral where we have a delta function. That is great, because that is the easiest type of integral to solve. So what do we know about the integral here? Well, since we have a delta function here, which is non-zero when u is equal to v, and we integrate over u, we simply pull out the rest of the integrand when u is equal to v. Right? So we have a delta function. We integrate over u. So we replace u by v in the rest of the integrand. And that's the value of the integral. Okay. So the value of the integral here is, we should not forget the n naught over 2, and then h and t minus not u but v. Okay, and v because that is the value of u for which the argument of the delta function becomes 0. Okay, it has to do with the sifting property that we talked earlier. Okay, okay, so the value of the inner integral is easy. It's n naught over 2 h t minus v. Okay, we're almost done. So what we have left now is one more integral from minus infinity to infinity, and then we had n naught over 2 h t minus v, and then the rest of the integral to the right here is also h t minus v. So we have it squared, and this should be integrated over v. So we simplify this by pulling out the constant n naught over 2, and then we have the integral from minus infinity to infinity of h squared t minus v dv. Okay, finally, what is this? It's a property of the pulse h, namely its energy, exactly. So the fact that we have shifted this a little bit along the t-axis or v-axis doesn't matter at all. So we just integrate the square of it for all possible values of the argument. So this is just the energy of the pulse h. Okay, so the fruit of all our labor is that we now know the variance of WT, and it's n naught over 2 times EH. Okay, and I think we deserve a break. So let's take 15 minutes.